Welcome, everyone. We are all together at the second online Cutting Edge lecture. We are located on the traditional lands of the Haudenosaunee and the Anishinaabe nations. McGill respects, honors, and acknowledges these nations as the traditional custodians of the lands and waters on which we meet, work, and enjoy each other's company today. And pretty much for a while now, we're going to be doing this. We will start tonight with the introduction to the speaker by Dr. Heather Mcshane. This was going to be the cutting edge that was going to be given face-to-face on March 24th. So it is rescheduled now. It will be online. It will be recorded. And then in about a week, you can watch it after it's cleaned up and edited. You can watch it on the McGill's YouTube channel. That's where all the cutting edge presentations that are online will be positioned there. There are some housekeeping things we need to attend to. Please turn off your microphones and your videos while Dr. Yajing gives her presentation. But if you have questions as she's presenting, use the chat function. That's a little icon on the bottom middle of your screen. It says chat, or if you use and it looks like a little bubble. And if you click on that, you'll be able to go into the chat room and type in your question. We will be taking those questions and using them after Dr. Louise's presentation. Frederic Guichard from Biology will be moderating our Q&A. He will use your questions positioned in the chat and pose them to our presenter. There is also a bit of a privacy issue that I have to alert you about, and you were probably, I hope you saw it written on the reminder that you were sent yesterday. If you join this event on Zoom, you and your child's name may be visible to other Zoom participants in the participant list and in the chat. This information will not appear on the YouTube live stream or the recording. So it is safe, just so you know. Some of you might be joining this conference on YouTube. I doubt it. It probably is not accessible there. And the same conditions apply there. So it's at this point that if you really don't want to participate, you would have to actually leave now if you didn't want any of that visibility obvious. So this is now our chance to welcome Dr. Heather Mcshane from the McGill Sustainable Science Institute, or MISSI as it is known. She will now introduce our speaker for this evening.
Thank you, Ingrid. So hello, everybody. I am, as Ingrid said, I'm Heather Mcshane. I'm the Program Director of the McGill Sustainability Systems Initiative. And it's my great pleasure to introduce Professor Yajing Liu from the Department of Earth and Planetary Sciences. And so she did her undergrad at Peking University, and then she did a PhD in seismology at the Earth Sciences Department at Harvard University. She came to McGill in 2011 to join the Department of Earth and Planetary Sciences. Her work involves numerical modeling and field studies. Her field studies are in the East Pacific Rise and the Cascadia subduction zone. And if, like me, you're not totally familiar with those, I can tell you now that I have looked up in Wikipedia. The East Pacific Rise is a mid-oceanic ridge and tectonic plate boundary located along the floor of the Pacific Ocean that runs off the west coast of the Americas from the Gulf of California to Antarctica. The Cascadia subduction zone is a tectonic plate boundary that stretches from northern Vancouver Island all the way down to the northern California. And interestingly, tectonic processes in this zone affect Vancouver and Victoria, as well as Seattle and Portland. And this was the zone that was responsible for the 1980 eruption of Mount St. Helens. So with that, Professor Liu's fieldwork involves taking cruises off the coast of Oregon. So it's a hard job, but somebody has to do it. She was supposed to be on a cruise late this month. So one of the very few positives from the COVID-19 outbreak is that because this cruise was cancelled, we're lucky enough that Professor Liu is available to talk to us today. So with that, I'd like to introduce Professor Liu to talk about slow and fast earthquakes from plate boundary faults to hydraulic fractures. Thank you, Professor Liu.
Thanks, Heather, for the really nice introduction. And I feel like you've already talked about the first 3 slides of my talk here.
Sorry.
So great, we'll be very good on time. And also I want to apologize ahead of time if there is any noise in the background because it's dinner time, the kids are running around. So yeah, just excuse me for that. Yes, so as Heather was introducing that, what I'm planning to do today is to introduce a bunch of research activities that I've been doing here at McGill in the past about 5 years or so, looking at earthquakes, but not just the dynamic fast earthquakes, but also slow earthquakes, a new phenomena that's been discovered in many subduction zones, and possibly in oceanic transform faults. That it's one of the research focuses in my group. And I also want to kind of bring you from the large plate boundary faults to areas that has smaller earthquakes but very actively happening due to the hydraulic fracturing for the shale gas exploration. So I just want to quickly say that this is a big collaboration or many collaborations with people who are currently at the McGill or students and postdocs in my group, as well as people who were here but are now at different places, and some of the colleagues that in the institution that I used to work at. Okay, so since I set myself up for this really ambitious title, looking at slow, fast, and from big to small, I feel like I should really do a brief introduction of the space and time scales of the earthquake source problems that I'm interested in. So on this horizontal axis, what you're seeing are a broad scale in space that we're looking at earthquakes that are happening at millimeter or even smaller scales of microfractures, for example, from the hydraulic fracturing activities, and all the way to plate boundary faults that are over thousands of kilometers long, such as this one here. This is the San Andreas fault that separates the Pacific plate to the west and North American plate. So we have over 9 orders of magnitude in terms of the spatial scale. And on the time scale or the relative movement rate, or how fast that 2 blocks are moving with respect to each other, we also have almost, actually over 10 orders of magnitude. So at the bottom here, we have what we call as tectonic loading, such like this case that the 2 tectonic plates are moving against each other at about 40 millimeters per year in total. So that's the millimeter per year time scale that we're looking at. And the whole loading process could change from tens of years to hundreds of years, or even over 1,000 years. This is the slow loading process that builds up a lot of strain energy towards the next earthquake rupture. And then rising up here all the way across 10 orders of magnitude, we have dynamic earthquakes that are happening within sub-second or to several minutes of time, depends on the magnitude of the event. Like for example, it's a really small earthquake, magnitude 0. The total duration of that rupture could be just like 0.01 second. But if you move across this entire scale to a magnitude 9, such as this Tohoku earthquake in northeastern Japan in 2011, that has ruptured an entire margin, subduction margin of nearly 1,000 kilometers with a total offset of more than 60 meters. So that's the kind of scale that we're looking at in both space and time, we're looking at about 10 orders of magnitude difference. Now, across those broad scales, we have something what we call as post-seismic relaxation. So this is the phenomena that could last only for a few minutes if it's really a small earthquake, or could also last for several decades. Such as of today, we're still seeing the post-seismic relaxation from that magnitude 9 earthquake in 1960s from the Chile subduction zone. So this whole post-seismic relaxation process is kind of going on in the background as we move from different tectonic boundaries. And what's really interesting is the discoveries happened that in the past 20 years or so is starting to fill this kind of broad spatial and temporal domain of what we call earthquake source scaling is this slow slip earthquakes or slow slip events. The first discovery, or one of the first discoveries, was actually coming from Canada. This is reported by the group from Pacific Geoscience Center in Sydney of British Columbia right here. And I actually showed this map, or one of those maps in my class lecture today. So what you're seeing here, let's move to the first top here. What you're seeing is because of the subduction of the Juan de Fuca plate toward North America. So with respect to a stationary station, say here in Alberta, that the station in Victoria is generally moving, being pushed toward the northeast direction. So at the bottom here is the east component of that continuous GPS time record since 1994. That was when we started to have continuous GPS time series, and until 2010. So this general trend is what we would expect because of that push from the Juan de Fuca plate. But what's interesting is, for example, in the summer of 1999, this particular station, actually several other stations, somehow decided to move backward toward the ocean. So that's this red arrow here that's pointing this seaward movement, which is opposite to what it's supposed to be, moving toward the interior of North America. And on the GPS time series, that's this little reversal that we saw here. So this is really puzzling because it's kind of showing that a motion on the tectonic plate that's doing in the same direction as if an earthquake would have done, except that this motion was so slow that it releases about 2 centimeters of slip, but within 4 weeks of time. So that entire duration is slow enough that it didn't really generate a dynamic earthquake, and that was why it was put here on this domain in this corner. And the same kind of phenomena or similar time phenomena that's accompanying the slow slip events is what we call as low frequency earthquakes. They're very similar to our regular earthquakes, except they're a little bit slower or a little bit longer in terms of their duration. So that's putting them together, we call them episodic tremor and slip events. And if you look at like northern Cascadia, they happen pretty regularly every 14 months or so, which is really kind of puzzling us and triggering us to ask this question, okay, what exactly the tectonic plate is doing, right? It's slipping at a further deeper down dip from what used to be what we call the seismogenic zone. So if it's loading up the fault, how is it going to affect the generation of the nucleation process of the next McGill earthquake? So that's why we think that the slow earthquakes here, in addition to the dynamic earthquakes, are a new but very interesting phenomena because it starts to fill this big spatial temporal scale and allows us to look at earthquake slip problems or deformation problems as a continuum a problem instead of just two extremes of one dynamic event here and very slow tectonic loading. Now, so to show this kind of broad scale problem, and what I decided to do today is to introduce a piece of kind of research from different kind of environments that I have worked on. One is from the subduction zone, and Cascadia is an example, and the other is from the oceanic transform fault of the East Pacific rise. Heather already told you what is oceanic transform fault, East Pacific rise. That's great. And finally, moving to the smaller scale, looking at how hydraulic fracturing are inducing earthquakes. Okay, so first, the Cascadia subduction zone. We actually know that Cascadia had ruptured in about a magnitude 9 earthquake in 1700. And we have that information because we have some indirect measurement versus direct records from the Cascadia margin. So before I show you the measurements, I want to first just introduce quickly the kind of deformation that we are expecting for a subduction zone. So for example, this is your subduction plate or fault. And because of friction that's acting along the interface, so that's the two tectonic plates are stuck together, and then which causes the upper part or the near trench part to be uplifting, and then the further inland was subsidence. Let me just go back a little bit here. And when an earthquake happens, this dynamic release of the strain energy is going to cause first vertical deformation near the trench, and this is the source for generating huge tsunamis. But in addition to that, we also see a subsidence a little bit further inland, as well as uplifting as we move toward the plate interior, which is off and compensating what's the deformation that because of the friction during the strain accumulation period. So because of that kind of deformation pattern, so when an earthquake happened, first we're going to experience, if there is a large vertical deformation near the trench, big tsunami waves. And that's been recorded not on the Cascadia margin, at least not from written record, but across the Pacific Ocean in some of the coastal villages in Japan, that they had written record of large tsunami waves, but no apparently felt earthquakes. The other indirect direct measurement from Cascadia are those ghost forests in Oregon and Washington. And the idea is that when you have the subsidence of this foreland region, they're going to submerge the vegetations and stop the forest from growing. Sometimes you don't really need a direct subsidence. There could be the ground shaking itself could trigger landslides, such like in this case here, that landslides would also make the subsidence the forest and again stop the tree rings from growing. So by looking at the tree ring growth pattern, and especially try to date when the tree rings stop to grow, that's one of this kind of a paleoseismological method trying to determine when a dynamic event might have happened along the margin that caused the subsidence of the ground. And finally, there are also native stories about ground shaking and flooding, but then because there is no written record, so it's not as like obvious evidence as those documents in the Japanese villages. The ground shaking itself also could trigger submarine landslide. So like as a wave is coming, or earthquake waves are coming, there might be landslide that's along the continental shelf, which is going to carry sand or other sediments in the current flow, deposit on the seafloor. And then if you could try to drill into the sediments and identify the locations and also date the occurrence time of what we call as the turbidite deposits. That could also give you some information about when a dynamic earthquake might have happened. And this is what's been kind of reported in this USG's open file report, where they look at along this entire Cascadia subduction margin, so going from the south to the north, went into the Wanafuga plate, did sedimentary drilling, and then dated when the turbidite deposits were identified in their drilling samples. And on this horizontal axis here are the dates of the turbidite deposits. This goes from current day to about 10,000 years before. So if you find a turbidite deposits in one location and then another location, or even a location that's hundreds or even 1,000 kilometers away, they are concentrated at a very narrow time span. And of course, this carbon-14 dating has some error on it, as you can see in the error bar. But if those, there is a temporal correlation between the turbidite layers across a large scale, hundreds of kilometers of scale, this is strong evidence that this dynamic event might have happened across the entire margin. So taking that data into consideration, Goldfinger and et al., they proposed that the paleo-earthquake history for Cascadia might consist of different kind of rupture patterns, that you could have the entire margin rupture, which repeats roughly every 500 to 600 of years, or you could also have part of the segments being ruptured, resulting in smaller and smaller magnitude of events with more frequent occurrences. So this is the paleo-earthquake history for the Cascadia, what we know about the past 10,000 years. Now, as we move to the modern history for Cascadia, when we started to have our global seismic network from the 1960s, so what I did here is I went to GeoMap app, which is a software that I use for teaching. I'm glad to see a student in the audience today here too. So this is exactly what we use to illustrate the distribution of global earthquakes. And I plotted up all the earthquakes with magnitude greater than 5 along all the subduction zones around the Pacific Ocean. So if you take a tour from Alaska to the Aleutians, to the Kuri Trench, to northeastern Japan, southwestern Japan, the Izubuni Mariana Trench, and all the way down to the Tonga Trench, and then come back here to South America, Central America, across the San Andreas Fault, back to Cascadia. You probably noticed that Cascadia is really an outlier in terms of generating the abundance of earthquakes. In all the subduction zones, we have a lot of earthquakes that are happening all the time, large and small ones, but Cascadia is really peculiar. If I zoom in Cascadia, you can see that Cascadia is very, very quiet. There are very few earthquakes have been recorded, and then the few of them recorded are quite deep, so we know for sure that they are not lying on the subducting interface. So this is one of motivations for the Cascadia Initiative project that happened from 2011 to 2014, which is to deploy a large group of onshore and offshore seismic and geodetic instruments to try to capture what the lack of seismicity is. It because that we just don't have much of coverage for the seafloor, or is it really just so quiet? So I was part of the cruise, and there are many cruises involved to get the seismometers on the seafloor and get them back. I was involved in the cruise in 2013 to deploy about 30 OBS on the continental shelf offshore of Oregon, and also a few others in the further deeper ocean. I'm really happy because preparing the talk gave me the opportunity to go back to my picture deposit and try to dig up some of the memories from that cruise. So this is taken on the cruise. This is from the Oceanus, which is a research vessel that we used for that time. And what you can see here, each of them is one OBS package. And here, what I'm showing you is actually what we call it as a troll-resistant system. So because a lot of the seismometers what we put in on that cruise was on very shallow water on the continental shelf, where fishing activity was really high. So unfortunately, sometimes that the fishing also fished OBS, ocean bottom seismometers. So the Lamont Earth Observatory Network, which is part of the Columbia University, designed this troll-resistant shell, which is basically the housing unit for keeping all the OBS components inside it and won't be screwed up by the salmon fishing or other kinds of fishing activities. And then so the different kinds of OBS are deployed through different mechanical systems. You could either through a wire, which is going to go all the way down to the seafloor and then release, or could also through a free release. So you make the package touch the seawater through the crane and then just release the hook, so it will just drop by gravity all the way to the seafloor, hopefully to sit at the stable spot on the seafloor. This is how the cruise kind of science room looks like inside the ship. So the most important thing is to make sure that your laptops are stabilized by the elastic string. And I think this is Jeff McGuire, one of my collaborators that you saw on the first slide, and that should be me based on the shirt that I was wearing. Occasionally we got company, which is really cute to watch. Sometimes that the crew decided to fresh up the kitchen menu. I think this is a final picture that I have here that's actually showing a very happy Jeff McGuire looking out on the deck, because that's the day that we finally see the land again after 2 weeks on the sea. Okay, so I'm coming back to the data. So the general finding from the using the Cascadia Initiative ocean bottom seismometer data is actually confirming that the Cascadia, the bigger part of Cascadia is indeed very quiet, except for when it comes to the Mendocino triple junction, which is where it starts to transition to the San Andreas fault. So that's when one of my grad students, former grad students, Duo Lee, started to combine those OBS data with stations on land, and then look at, well, how do those earthquakes distribute with respect to the subducting interface, and also what kind of focal mechanisms do they represent. So I'm going to spare you with all the details, but really want to point out is first that there are lots of seismicity, but most of them are indeed actually happening in this deeper mantle layer. So that's beneath the subducting slab, which is puzzling again because the mantle materials are supposed to be stronger than the subducting fault. The reason it's called a fault because it's already broken before, it's supposed to be weak. And then there are also a bit of seismicity in the overlying continental crust material, but very few that are sitting in the subduction zone itself. So what we did in that work really is try to use all the focal mechanism solutions that we could get our hands on, and then try to estimate what's the direction of the maximum compression. Okay, so you don't have to worry about all details here, but really just focus on the red dots on this plot here. They're showing what's the maximum compressional direction for the upper crustal layer in the continent, and for the lower mantle layer. And here I'm trying to illustrate the contrast. Really what we found from this study is that in the continental crust, the maximum compression is coming in roughly this east-west direction. So that's kind of consistent because we have a subduction zone going on. So you're expecting compression is coming generally in this southwest, northeast direction. But as soon as you cross the subduction fault, you step into a margin, a region in the mantle where the maximum compression now is actually pointing in or out of the board. So it's perpendicular to my screen right now. I'm using this little arrow here to point to. So having that kind of fast change in the maximum compressional direction tells us that this subducting interface itself must have been really weak to allow this rotation to happen in such a short distance. And we did some more statistical analysis of the directions, and we came up with an estimate that the plate boundary fault itself, this plate boundary fault itself, must be very weak, and then the upper limit of its strength is on the order of 50 MPa. And given that, and given what we know of the past magnitude 9 earthquake in the 1700s, we're also making the implication that whatever stress that has been released from that magnitude 9 earthquake has probably already been recovered, suggesting that we're coming to the end of this Cascadia max thrust earthquake cycle. So that's my Cascadia story. I want to move quickly now to its specific rise, as Heather already introduced, that oceanic transform fault is a strike-slip fault that offsets two mid-ocean spreading centers. And they're really nice to study because, especially the fast spreading ones, like this Clipperton from EPR, because they're spreading really fast at more than 100 millimeters per year. So in order to generate the same magnitude of earthquake, and you're slipping at the fast rate, it means that you don't have to wait for another 500 years or even 50 years, which is already like longer than my career probably, to get to observe the next earthquake. So that's why we decided to choose this GOFAR discovery and Cabrera further to the east, this transform system from EPR, where the spreading rate is 140 millimeters per year. It's one of the fastest spreading centers on Earth. And because of that fast spreading rate, if you look at this plot here, this is plotting the earthquakes of magnitude 5 and bigger on this western segment of GOFAR from 1999. So what we're seeing is a very regular pattern of earthquakes that are happening every 5 years or 6 or so, to the point that we can actually predict, I mean, this was back in 2006, 2007, we predict that the next earthquake would happen in 2008. And that's how we decided to carry out this 2008 Cabrera Discovery GOFAR OBS experiment as the first local observation of oceanic transform earthquake cycle, which we actually caught this the magnitude 6 earthquake that we predicted would have happened. So that whole experiment involved 3 cruises, about 74 days at sea. I mean, it's not a continuous 74 days because we have to put them down and then went back to take them back after about a year. So these ocean bottom seismometers, because they are sitting on the seafloor, and they have to rely on battery to survive, and the battery is really kind of determines the lifespan to be roughly kind of half to 1 year time period. And in addition, we also did 2 refraction lines. So they're basically kind of doing the ocean bottom active source exploration and try to see what kind of properties are varying, not just along the fault, but also across the fault. So the entire cruise caught about 70,000 earthquakes, including that big magnitude 6, and it's 20,000 foreshocks, which allows us to confirm our kind of observation or confirm our implication that we derived from all the previous teleseismic earthquake data, is that this rupture, magnitude 6 rupture, is really limited to a small segment, about 20 kilometers along the fault, and then it's straddled by what we call a rupture barrier zone, not just to the east but also to the west. I think the west part is especially interesting because when you think about it, it's already right next to a mid-ocean spreading center, where, as we understand, it's where the magmas are rising and express themselves to the seafloor, solidifies to form the newest oceanic crust. So the temperatures here are so high, and they're not supposed to be to accommodate a brittle failure. So I think our observation here of active seismicity here really kind of points to a very effective mechanism, as we call it, a hydrothermal circulation. So the idea is that if you have a very porous material and seawater is able to circulate within the oceanic crust, the porous oceanic crust, to a greater depth, and that water might be able to actually weaken not just the oceanic crust material, and if it comes further deeper to the mantle materials, it could continue to weaken the mantle materials and make the seismicity possible in at that kind of depth. So yeah, with that information and as well as the refraction data that shows this low velocity zone across the fault, we hypothesize that, well, maybe there is a mechanism, dilatancy strengthening, that's helping to stop the earthquake from rupturing further toward the east. And the idea is that if you have fluid saturated granular material, they're highly packed together, and as you try to accelerate shearing across each other, those particles will try to rotate against each other, which temporarily opens up more pore space and temporarily drops pore pressure, which actually makes the two sides of fault to be compressed against each other at a greater strength. So that's what we call as a strengthening mechanism, which could stop earthquakes from rupturing. And it's a mechanism that many people have studied before in different environments. That's what we took into a numerical model. So here's my first bit of numerical modeling, is take that mechanism into the earthquake cycle model. Again, don't worry about the details, but really the key results here is that the dilatancy is able to stop earthquakes from rupturing across this barrier. So you see that the first earthquake is limited to this area and then waited for about a year before the second earthquake ruptured this area. The other thing that kind of unexpected from the modeling is what's happening within this central zone. We used to be thinking that it's just happily creeping against each other, but in fact, what we see is this kind of slow SIP events that are also happening from the model. And then we can calculate like how fast the slow SIP is propagating along the fault. So each of the line here is my modeling, numerical modeling results, but they agree so well with this seismicity migration that we observed from that OBS experiment. So we hypothesize again that there are also SIP events, just like in Cascadia, but here on the oceanic transform fault, and that slow SIP itself is driving the migration of the seismic swarm activity. So this is all good, but we really want to kind of go back to GoFar to confirm whether our ideas are right or not. So that's a time that in 2017 we started to write another NSF proposal to go back to GoFar. We actually call it GoFar Transform Fault Earthquake Prediction Experiment. And that proposal was funded in the first attempt in 2018 that we know we were funded, and we started to prepare for our next cruise. And it was around that time that what we predicted would happen and wanted to catch, that the 3 magnitude, roughly 6 earthquake that happened in a very close time window. And we were really disappointed, right? We probably missed our target before we could get our stations there. But then we looked around and we found that, well, maybe on this eastern segment of GoFar, there's still a very tight time window that we can fit in. So we changed the cruise schedule like very rapidly and decided to put most of our OBS on the eastern segment of GoFar instead of the western original planned. So that happened last year, the end of last year. The stations are still there, and we were really happy. In March this year, March 22nd, I think, we were exchanging happy emails around that day because that magnitude 6.1 did happen as we predicted, as we hoped, and was well captured by all the stations that we put in down there just a few months ahead of time. So that was a very successful, I think, prediction experiment. But the thing is that we now, because of the COVID travel ban, none of the international collaborators will be able to get on the next cruise to get the data back. And to me, it was really kind of a big disappointment, or for lack of a better word to put it, is that not only the OBS experiment itself was really interesting to me, but also the second cruise actually had a Sentry, which is an automatic underwater vehicle dive that's planned with it. So a Sentry gives you a really high resolution size scan of the bathymetry of the ground, and it can also identify, for example, hydrothermal vents on the seafloor. It operates to up to 6 kilometers on the seafloor, so just a bit short of the Arving, which is the one that you can actually dive with. So that's kind of a disappointment, but hopefully that we're going to get all the data back still in time and be able to analyze this magnitude 6 earthquake. So I think because of the interest time, I'm going to quickly go through my induced seismicity section here. That just to point out that McGill, my research group, started to look at hydraulic fracturing earthquakes in northeastern BC in the mountainy basin from about 3 years ago. And the first order of results that we got from that is an order magnitude increase in terms of the number of events that we have detected. For example, the Canadian National Network reported only 64 earthquakes within that period of time, and our catalog has nearly 5,000 events. So that gives us a lot of information in terms of where the earthquakes are happening and how they are related to the injection activity in the nearby area. So I'm just going to quickly jump through the slide here, but show you this picture that from a very recent study from one of the students that I work with. Is because now we have this high resolution image of the spatial and temporal of seismicity, so we can really see how the earthquakes are migrating as the hydraulic fracturing stages are moving from the distal end of the well and toward the well pad, which is they drill the vertical well and start to deviate into horizontal wells. And another interesting observation here is that if you put all the seismicity observed and on top of each individual injection stages along the wells, you can see that some of the injections were very active in terms of generating earthquakes, but we also have a lot of, or several of the wells that nothing has been observed. So this is really kind of a $1 million question that waiting to be answered is, what are the conditions that would make one well becomes seismic, or injection from one well becomes seismic and from the other well are aseismic? And this is really kind of a key question to a lot of practical operations in the field, such as the traffic light system that determines whether the operation needs to be suspended or can go with caution. Like, for example, if we look at Alberta has a traffic light system where if an earthquake with a magnitude 4 is induced, then everything has to be stopped. And then if it's in the magnitude range between 2 and 4, then you have to mitigate your operation. For example, reduce the volume of injection or reduce the pressure of injection. Whereas in BC currently, they only have a stoplight system. So anything with magnitude lower than 4 can go ahead, probably with some reporting going on here in the orange zone. But anything upper or greater than magnitude 4 will have to be stopped. So having that kind of information, the detailed information from this field monitoring really can give insights to how to better design the kind of traffic light system to minimize hazard. Okay, so I think I'm going to quickly summarize here of a lot of things I try to fit into the talk. hopefully that at least there a bit of information that you can take away. And the research is supported by NSERC, by NSF for the oceanic transform fault part. McGill also generously supported part of the research, and BC Oil and Gas Commission provided really valuable logistic support so that we're able to put the stations on the ground. Finally, I want to thank my spouse, who is not here, but he let me use his study so that we can have a relatively quiet environment to go through the talk. I think I'm going to stop here, and I'll be happy to take questions if there are any. Thank you.
Thank you, Professor Liu. And thanks for a great talk, very interesting. And so we had some questions from the audience, and I will start with those. So someone asked if do slow slip events, so that was, I think, referring to the beginning of your talk, do slow slip events mean that rapid, dangerous earthquakes will be less likely to occur because stress is not built up?
That's a great question. I think the answer to that question is two parts. It depends on where the slow slip is happening, right? So if the slow slip is happening in what we expect to have large earthquakes, then you're absolutely correct that the slow slip is already releasing part of the stress, but in a slow motion. So what's left of that stress when it's released in the next earthquake will not be as damaging or as powerful. But the second part of the answer is that if the slow slip is not directly within the area that you're expecting your next earthquake, if it's next to it, then having a slip here is actually going to load up your neighbors, which would add up to the stress and then probably either advance the timing of the next earthquake. So having a kind of a better resolution in terms of where the slow slip is happening is extremely important for that kind of consideration of hazard. But that's a great question. Thanks.
Yeah. Great questions have complex answers. That's the rule. And so there's another interesting question. So which of the two large cities in the Northwest, so you talk about Vancouver and Seattle, would be affected most in the next big earthquake in the region offshore? That's I don't know if it's a $10,000 question.
Well, so I don't know if you guys were actually aware of it. Today, October 15th, is actually the Great Shakeout Day. So BC is a big participant in the activity. So the activity really it started from Southern California, and I think it's quickly becoming a global activity. That on October 15th at 10 o'clock 15 minutes, that we are whoever was signing up to participate would practice this drop and cover, hold on. That's like the 3 steps that everybody is supposed to be doing if the earthquake comes. Wow. I think in terms of a lot of the answer to that question, I think lies in first infrastructure, like how the infrastructure is prepared for the kind of shaking. So Seattle and Vancouver are not very far from each other. If we do have a magnitude 9 earthquake coming from Cascadia, the kind of shaking from the earthquake source itself is not going to be very different, but then the local geological conditions of where the individual buildings are sitting on is going to make the difference. So whether the building is sitting on unconsolidated sediments versus solid bedrock is going to make a difference. And also the building structure itself, depending on the year that it was built and then the safety code that was effective at that time also has a big difference. So that would be, and then in addition to that, the population's preparedness to a big earthquake rupture also plays a difference. Yeah. That's why we should all participate in Great Shakeout.
Cool. Yeah, thanks. Maybe that brings me. I had a very naive question for you. If I just take the one thing I would imagine as being important in earthquake science is from childhood and movies and its predictability.
Yes, prediction. Prediction is the holy grail.
Please, and predictable nature of them. But then listening to your talk, I kept seeing slides or data that showed periodicity, periodicity is predictable. And so is that what's
only to some extent,
and the unpredictability of big earthquakes in general?
Yeah, so I mean, it depends on how precise you want the prediction to be. Yeah. Right, so I talked about like we were brave enough to put prediction experiment in our NSF proposal, and we were lucky to be funded. But like a precise prediction involves where exactly, when exactly, and how big exactly it's going to be. Yeah. And I don't think we are at that stage yet. I mean, kind of optimistic yet to make that kind of prediction. But to back off a little bit, like we were really successful in terms of predicting the next magnitude 6 earthquake on the Gulf Fire Transform Fault in terms of when approximately it's going to happen, where approximately it's going to happen, and how big approximately it's going to be based on the knowledge that we collected so far. Mm-hmm. So a lot of kind of research motivation is try to reduce the error bar on those predictions. Mm-hmm. Yes.
Thanks. I would invite the audience, if you have a question that you didn't put in the chat, you can unmute yourself and ask your question for Professor Liu. Otherwise, you will be stuck with another question from me, because I have many.
Great.
About it, I'll ask another question. Think about that option. But I was interested in the last part of your talk. You talked about these injection activities that are on your temporal scale, on your temporal spatial scale events. They're like these tiny events, I guess, that are really fast, and they can trigger seismic activities. And the way it's managed, it's, well, if it can trigger a big activity, then we don't do it, we stop. If it only triggers small activities, we're good. But do they have a cumulative effects that if you let go small activities, and so that's fine, they don't trigger big seismic activities, is there any cumulative effect that they could have in the long term, a more massive effect?
That's an excellent question. It's like, could one of the small earthquakes grow into a big one? Yeah. Right? Like if you continue to be pumping thousands of cubic meters of water per day into the ground in 2 to 3 kilometers, and you're doing that, like every horizontal well has like 50, 60 stages, and they do multiple horizontal wells from each of the vertical well pads. So that's a lot of volume of fluids being injected. So I think that the answer is I didn't have time to show that particular case of a magnitude 4.5, which is the largest earthquake that we've observed during the time that we have our network there. And it's also the second largest hydraulic fracture-induced earthquakes in Canada. The next one, the largest one, was a 4.6, just slightly bigger. So for that particular earthquake, based on our data, what we think is what happened is the injection was happening at a depth about 2.2, 2.3 kilometers. But then somehow the fluids find a hydraulic permeability conduit. So that's like kind of like think about a pipe that allows fluids to go from the shallow depths to deeper depths at a very fast rate. So that fluid conduit channels a lot of injecting fluids into about 4.5 kilometers and hit what we call as a pre-existing fault. And that was how we think that have triggered this magnitude 4.5 earthquake, because there was already a fault there, and you have channel of fluids onto the fault, which sort of acts as a lubricating effect that triggered a slip on it. So even though a lot of earthquakes that are really next to the injection wells at like 2-3 kilometers, they're small. But if you have a mechanism to channel the fluids to a pre-existing fault, which is larger compared to that meter or millimeter scale of little fractures, then that could lead to a larger magnitude event.
Oh, interesting. Thank you. Yeah. So it is now 7. So I will stop the question and thank you again for really interesting talk and discussion. Thank you very much.
Great, thank you.
And I'm supposed to turn the microphone back to Ingrid now.
Yes, thanks, Fred. So it is my turn now to officially thank Yajing for her talk, and I'm going to, as soon as my video is on, I'm going to hold up the present that was already wrapped up for when she was supposed to give the talk in March. And I wrapped it, so I do get to unwrap it. So I did wrap it with McGill paper, and we always had a very nice thank you card branded for video for the cutting edge. I did unwrap it, Yajing, and I will send it to you for the speaker. We have the Treasures from the Earth. It's a publication from the Red Path Museum.
Yes.
So it's all the minerals and rocks in the Red Path Museum gallery. But for your children, I'm including, because they had to be part of this, this is the Red Path Museum coloring book.
Oh, that's so great.
I think you have 2 children, am I right?
Yes, I do.
So you have to send me privately your home address, and I will put that in the mail. Canada Post is working; it's safe, and your home address will be safe with me. I will not share it with anyone.
No worries.
For our audience, I'd like them to, if voluntarily, if they would like to show earth-shaking but visually muted applause by turning on their cameras and giving a very nice round of applause for our speaker, Yajing.
Thank you. Thank you all.
Very interesting talk. In a month from now, Thursday night, November 12th, we will be back together again, but you do have to pre-register. You have to go on to the Red Path Museum website, look for the tab that says Cutting Edge, and there is a pre-registration site, and then the Zoom link will follow that after you've pre-registered. The speaker, November 12th, is Kyle Elliott. He's from Natural Resource Sciences. He is presenting a very interesting talk about his cutting-edge research with birds. He attaches all kinds of monitors to birds that fly very long distances, and in order to understand how they do this and somehow come to some sort of understanding of how they are able to even navigate. So that's November 12th. We'll see you back here, and in about a week, if you need to see this recording or share it with your friends, just log on, and probably by next Friday, the 23rd of October, log on to the McGill's YouTube channel and see if you can find this recording. Share it, share the link to participate in the series, free, brought to you by McGill Dean of Science, Bruce Lennox. Thanks, everyone. Time to say goodbye.
Bye, everyone.
Bye. Thank you.